Good morning. Are we ready? Ready to go. Okay, so we'll start as usual with some administrative notes, and I'll leave the stage to Joelle so he can explain you how the hardware exercises are going to roll out. Go, Joelle.
So, good morning, everybody. So we are extremely happy to announce that 110 students subscribed to the hardware exercises.
Sorry a sec, I'll interrupt. Just for curiosity, could you please raise your hand if you signed up to the hardware exercises? Okay, so pretty much everybody in the room signed up for it. Okay.
Okay, the other ones can still sleep for 5 minutes. And so we have 5 students per group. The groups are formed. They can be found online in the homepage. If you were assigned to a specific group, which is not the one you signed up for, write to the leader of the group so that you can meet the members of the group. So how this will work? We will have 2 rooms. One room is J44.4, and the other room is F44.2. And this will work as follows. So there will be a room with no TAs. This is J44.4. There will be computers, and you can always work there during normal ETH times. And then there will be 10 2-hour time slots in the F44.2, where there actually will be a TA, which is helping you if you need. You can sign up for these 2-hour time slots in this, following this Doodle link. You can find the link also on the homepage. And for the sign up is very important. I've seen that some of you already signed up. You have to sign up with the group number that you find on the homepage. So every group has a number from 1 to 22, and you have to use this group number in order to sign up. For the first sign up, I want you to sign up just 1 time per group. So there are more slots than 1 time per group, but first let's sign up 1 time per group, okay? All the details will be written a bit better in Piazza this afternoon. So we have to give you a bit more of information. Per slot, we will need 3 groups, which means if you see that already 3 groups signed up in Doodle, you cannot sign up anymore. And this is for safety reasons. So in this F44.2, there will be computers, there will be a Duckytown track to test your algorithms, and you cannot be there more than 20 people. So if you are the 21st person in the room, you have to leave.
Actually, okay? Sorry for the interruption. This is a fire safety constraint. You will notice, first of all, that F44.2 is in a weird location in the building. So I welcome you to go and check it out before you actually have your group time slot. And that whole wing, let's say, which are 3 or 4 rooms, they all have like a small corridor, so the 20 people constraint applies to all rooms, not just to one. But the other ones are mainly empty, so try not to crowd in there because the fire department could just kick us all out. Okay? It's not safe.
Yes, and the other part of the room, of course, they cannot enter. So there is a part of the room where there is the actual Duckytown. You can notice this because of the beautiful decorations. You cannot go there, okay? And we have security cameras, so Jacopo will be there.
Smile, you're on camera. Yeah.
Okay, so many people means many rules. We have some rules. First of all, hosting 110 students is not that easy, so we have prepared a big amount of hardware, a big amount of computers and stuff, so try to use them carefully. You don't have to disassemble parts of the hardware. In particular, don't touch the cameras, okay? Every Duckybot has a camera. If you touch the camera, the calibration is gone. So don't touch the cameras. Try to clean up after you go and to leave cleaner than you found the place. And no eating or drinking in the lab. So no snooty and swiri in the lab, okay? An important thing that actually makes Jacopo really angry, don't test the tracks with the shoes. So don't go on these Duckytown tracks with your shoes.
Always. You're welcome to take your shoes off, though. So these are all for functional reasons. It's like if you walk with shoes on the track, you'll leave grayish marks, and the Duckybots will interpret those grayish marks like lines and just go out of the road. Okay, so like it's
this is not in your
The
interest.
functional constraint.
Exactly. And then so the exercise will be self-explaining. So you don't have to modify files which are not set to be modified. This means don't try to go all over in Ducky Town environment and modify stuff because things easily break, okay?
If you want to do it, just ask a TA, and we'll put you in the condition to just play around with the code however you want. But in any time you have a doubt, just ask the TA. You have a question, ask a TA.
Okay, I think it's everything. Do we have already the dates for the come up of the exercise? No.
I think so.
Later.
Anyways, the details of all the logistics will come up later on Slack. Okay. Thank you very much, Joel. Okay, so any questions related to the hardware exercises before we move on? Yes, no, maybe? No. Okay, so let's get back to the course now. We have progressed through some of the course. We're roughly halfway through. Just to give an updated version of how things are going to happen, we basically today is going to be the last class on the analysis part of the course. That is, how are we going to, given a controller, given a system, how do we check if things are right? How do we check if things are stable, if they're performant? How do we interpret the behavior of systems? The second half of the course is going to be about synthesis. It's going to be about, okay, what if I have a plant? I have the performances now, specifications, and I want to actually build a controller that achieves those specifications. We will touch upon two of the main families of approaches for multi-input, multi-output control. It's not going to be exhaustive. There are many other methods to go about controlling MIMO systems. But we will talk about linear quadratic theory, in particular the famous linear quadratic regulator, or the LQG as well. And then we'll talk about H-infinity control, which is you start getting a hint about what is H-infinity. It's about minimizing worst-case scenarios, and we'll see how that works. We will have to shuffle some of the lessons around to provide you the necessary knowledge to do the hardware exercises. So we have constraints depending on when the hardware classes start, but everything should still feel logical as we go through. So today we will talk about stability, performance, and robustness for MIMO systems. Just a brief overview. This is the usual story. So the direction in which we're going is pretty much always the same. We started from CISO systems. We first determined, okay, what are the objectives of what we have to do, of designing a controller? Stability, performance, and robustness. Really important. I will say it every time. Then we looked at what stands in our way to achieve the objectives for CISO systems. And we saw that there are limitations, both of theoretical and of practical reasons. So the various constraints related to the sensitivity functions being complementary, or the Bode integral, that is the principle of conservation of dirt, as we mentioned it. And we see that we can't really do as we want when shaping the frequency response of the system, and therefore we can't just arbitrarily respect any kind of performance. Then we expanded a little bit the class of systems that we can discuss. We started talking about MIMO systems. So we stepped back for a second and we looked at what are MIMO systems? How are they different from CISO systems? They have multiple input, multiple outputs. This means that the matrices are a little bit more, have different dimensions. And since matrices cannot commute, this implies that everything we've seen before, we have to be a little bit more careful and consider the order in which we do things. So we introduced sensitivity functions both for the output or for the input. And we then looked at a little bit more structural properties of MIMO systems. And we noticed that up to now, pretty much everything, all the ideas that we learned for CISO systems still extend and apply to MIMO systems, but you have to be careful. So there's this concept of directionality. MIMO systems have behaviors that change a lot depending on the direction of the input and the output. So we wondered, what are these directions? And we looked at the singular value decomposition. That is this mathematical tool that we can use to break down pretty much any matrix and see what are the favorite input and output directions. But most importantly, we see the singular values. And the singular values represent gains in particular directions. We noticed that we lacked the tools to compare signals and understand what does it mean to have a large system or a small transfer matrix. And we developed norms. So we looked at two kinds of norms, basically. We called them the vector and matrix norms were spatial in the sense that they were measures that averaged through the components of the matrix or the vector. And we can imagine that to be an average over space in the sense of the different channels of the inputs and outputs. And then we looked at the signal norms and the system norms with the intermediate step of induced matrix norms, which take into account not only the spatial average of a system or a signal, but even the frequency or time component. In particular, we focused on two kinds of norms, the 2 norm and the infinity norm. There are many more norms. Norms are just operators that satisfy specific properties, but these 2 norms in particular are very useful engineering-wise because they represent either, respectively, the energy of a signal, the 2 norm, or the maximum singular value across all frequencies, the infinity norm. And since we know that the maximum singular value represents a gain, therefore, when we look at the infinity norm, the maximum gain in some direction, what we're looking at, of course, depending what signals we're looking at, but it could mean a worst-case scenario, like the maximum amplification of something we don't want to amplify, for example, okay? Today, we will look into stability, performance, and robustness criteria for MIMO systems. So we're just following the pattern we did with CISO, but now we're extending it to these new class of systems that we looked. So I briefly mentioned already the norms, but in particular, the 2 and infinity norms are relevant. One thing that it's worth mentioning is that the infinity norm, contrarily to the 2 norm, does respect the multiplicative property, we called it, so that the norm of a product of 2 systems is the lesser or equal than the product of the norms, which means actually submultiplicative property maybe is a better name so that we can remember it better. And this is a very important property because, as we will see today, it can be leveraged to reach a very important result, which is called the small gain theorem, that allows us to treat closed loop stability of MIMO systems in a very quick way. So yes, singular value decompositions, we saw that any matrix can be divided into a left singular value, singular directions, times the singular value matrix times the right singular directions matrix. The U and V matrices must be unitary matrices. That means each column has 2 norm equal to 1. And if you multiply the transpose by the other, you get the identity matrix. And we saw that the singular values corresponded to the root of the eigenvalues of the function, of the matrix that we're looking at, but multiplied by its transpose, basically. We saw that these singular values were helpful, as mentioned before, for identifying the main directions of inputs and outputs and the associated gains. And we saw that we could leverage this concept to find, for example, the directions of the main directions of poles and zeros. Because as for CISO systems, in MIMO systems, we do have poles and we do have zeros that have similar meanings and bring similar limitations to the performance of the system. But again, they have this concept of directionality involved. So a 0 is a 0 only if it's in a specific direction, the direction of the 0. And we could leverage singular value decomposition to find these directions, because a 0 is a 0 of a transfer function has the property that if you send a signal in that direction, you get the 0 output. So if we break down the transfer matrix into its singular values and singular directions, well, we will find that there is one of the singular values that is equal to 0, because that's the gain across that direction. So if a gain is 0 across a direction, that means that direction is the 0 direction. And a similar approach can be used, in principle at least, to find the directions of the poles. Unfortunately, this is a very ugly way of writing it. Any mathematician would fire me on the spot if I write it something like this, but hey, as long as we say it on camera, you can't never write something is equal to infinity. It's always like the limit reaches infinity. But the idea being that a transfer matrix evaluated at a complex position called the pole generates an infinite output. And if we just perturb a little bit that direction, so we don't look really at the pole, but a pole plus epsilon, and then we make that epsilon very small, we can very well approximate the directions of the poles as well. Just a few other remarks on singular values that are really important to recall. The lowest and the highest singular values, again, represent the minimum and maximum gains over specific directions, and they bound the ratio of the response of the signal, input to output. It's very important. So if we'll use this result directly as it is today to show, to define input-output stability of a MIMO system. So the ratio of the output to the input, or at least the two norms of the output to the input, is always bounded by the biggest and the smallest singular value of the transfer matrix. And then we defined the condition number, that it's simply the ratio of the biggest to the smallest singular value, as a measure of the conditioning, as the name suggests, of the MIMO system itself. And typically speaking, a MIMO system that has directions where the gains are very small, so the denominator of that condition number is very small, that means that it's difficult to control that direction or that associated output, while a big gain means that we can easily control that direction. So while it is not always very indicative, the condition number can provide information on how difficult it is to control a system. And then finally, we notice that singular values are a function of frequency as well. So let's talk about stability. So as we mentioned at the very beginning, the first objective of a controller is that of achieving stability in a system. How do we define stability for a multi-input, multi-output system? Well, for a CISO system, we said, look at the transfer function of the closed-loop system and look at the roots of the characteristic polynomial, which are the zeros of the denominator of the transfer function, or the poles of the system. And we saw that in order to have asymptotic stability, well, we just require the real parts of the poles to be negative. Since now it's not that straightforward, or is it not? In the MIMO case, we define two kinds of stability. The external stability, or the input-output stability, that is simply related, as the name suggests, to the magnitude of the output given a certain input. So if we think about two norms, we can say, if I send in a signal of unit energy, for example, how much does the output, change? How much is the energy of the output? Is it bigger or is it smaller? Generally speaking, we consider a system BIBO stable. That is, if you provide a bounded input, you get a bounded output. If I provide finite energy to the system, the output can't be of infinite energy. Otherwise, it would be unstable. For example, we can represent this condition with, we said that norms are just a measure of signals. So in this concept of bounded input, bounded output, we could use any measure of the input and the output to determine if the system is BIBO stable. So for example, infinity norms can do the trick as well. And it is possible to show that fundamentally the same things that apply for CISO system, conditions that apply for CISO systems, apply for MIMO systems as well. At the end of the day, to have external stability and input-output stability, you need all the poles of the closed-loop transfer function to be strictly negative, have real parts that are strictly negative. Are there questions? Doubts? Comments? No. So the small gain theorem is something that applies even to the CISO case as well, but it's not as useful, so you never heard of it. And it provides a sufficient condition to check for input-output stability. Sufficient means that you can try it. If it works, it's good. If it doesn't work, you cannot say the system is not stable. Why is it powerful? It is powerful because it is very simple. All it says is, let's say we have an interconnection of systems. We're looking at closed-loop stability of a system. And let's suppose that each system has a norm that is some positive value, gamma 1 and gamma 2. Then the interconnection of the systems is a stable, input-output stable that is, if the product of the two gains is smaller than 1. It's quite intuitive, I think, this result. the norm of a system represents how much we're magnifying a system in a specific, how much we're magnifying the norm of a signal. So if the product of the norms of the two systems is smaller than 1, it means that we have convergence. The systems don't get magnified as they pass through the loop. It's important to note that norms somehow kill signs. So you might notice that there are no plus or minuses in the interconnections there because they don't really matter. There is no phase information considered by this theorem. This small gain theorem is powerful because it will allow us to, by playing around with what are the L1 and L2 systems, it will allow us to define tests, practical conditions that we can easily verify in the case of uncertainty, when we don't really know what L1 and L2 are, as we will see later today. On the other side, well, input-output stability is, of course, necessary, and it's, of course, important. In MIMO systems, we want to look at internal stability as well. And the concept of internal stability is that of, let's say we have some input at any point in the system that we didn't plan for. We have to make sure that that input at any point in the system, it could be a disturbance, it could be a noise, it could be something on the feedback branch, doesn't just get amplified without we noticing. Because it is very possible that a system can be input-output stable, but some of the variables that we typically don't measure inside of the control loop grow to infinity. So how is this possible? Well, it is possible if in the multiplication of the various transfer functions, zero-pole cancellations occur. You might have heard about how zero-pole cancellations are really a bad thing in general, because they hide the behavior of a system. So mathematically, it is possible, for example, if you multiply a controller by a transfer function, you might just want to, I don't know, simplify out an unstable pole. Well, the fact that it's simplifying mathematically doesn't mean that it's not there. It means that it's just hidden from us, in the sense that we can either not reconstruct that behavior by looking only at the output. This is the concept of observability, which we have not really talked about yet, because I'm reserving it for when we will study state feedback theory. That's the next lesson, actually. But even the concept, we know well the concept of controllability. That is, can I send some inputs and actually modify that direction? Boiled down very much. When these cancellations occur, we might lose the ability to modify the behavior of one of the variables in the system. So we have studied sensitivity functions at the very beginning. I think it was like slide 7 of the whole course. And we put it there at slide 7 because they're actually very important. Sensitivity functions map all the possible relationships between all possible inputs and outputs of a system, not only the inputs like the reference signal and the output, but, for example, all the different mappings between the disturbance and the tracking error, or the input, or the disturbed input, or the noises, and we looked at all these sensitivity functions. So a system that is internally stable intuitively means that not only the input-output transfer function is stable, but all the sensitivity functions inside are stable as well. It is important to note that internal stability implies external stability. If all the variables that we typically don't measure inside a system don't blow up, well, for sure the input-output relationships won't blow up. But the converse is not always true. It is true only if the system is both observable and controllable, which is a complicated way of saying there are no zero-pole cancellations. It is possible to define an actual test to see an easy way to see if a system is stable or not. And the bottom line idea is making sure that the relationship between the inputs and outputs, the inputs and the internal variables. So if we look at this block diagram, that might look weird because we never looked maybe at something like this. But if you play around with it, and it's an easy and interesting exercise to do, you will see that it's very much the same old control loop that we write down every time. Internal stability means that if we insert some inputs, for example, omega 1, omega 2, W1 and W2, which could be references, disturbances, noises, then the internal variables of the loop don't go crazy, don't explode, don't go to infinity. How does that happen? It happens if the mapping, the transfer matrix between the W1s and the Ws and the Es, which is very easy to derive by just doing the usual algebra that we did many times at the board, so I won't repeat it today. That whole matrix has to be stable. And it can be shown that a necessary and sufficient condition for this to happen is that individually each one of those functions is stable. So you can check for internal stability by writing what is the relationship between the inputs and the outputs and checking if each one of those components has a stable transfer function. Note that even if 3 out of 4 are, or whatever, all but 1 are stable, that doesn't mean that the system is mostly internally stable. It means it's not stable, okay? If one thing goes crazy, then the whole system goes crazy. And by crazy, I mean grows unboundedly. So, okay, we've looked at how we define this. Yes, sir.
In the last slide, what exactly does rational mean when you talk about the matrix?
What does it mean, irrational?
Yeah.
The terms are rational polynomials. The denominator has a bigger degree of the numerator. I mean, there are fractions, and a proper rational fraction means that it's properly a fraction in the common use of the term proper, which means it's less than 1. So the denominator has a bigger degree than the numerator. So suppose a system is not stable, and what are we going to do about it? Well, we might want to design a controller to stabilize it, right? At the end of the day, the first objective of a controller is to stabilize the system. Can that always be done? Well, we saw in CISO systems that no, it can't always be done. You can't always define a controller such that you can arbitrarily set the performance of a system, including stability. But the system needs to be controllable. And to test for controllability, we saw that there was this, depending on, there are many different tests you can do for controllability, but the idea is that every input should be able to affect the directions of the system. And you can test easily by building the controllability function matrix, which has the same form as that for single input, single output cases. And the condition is the same. It has to have a rank that is at least the size of the dimension of the system. The only tricky part here is now that the C matrix, the controllability matrix, is rectangular, right? Because the dimensions of B are different than in the CISO case. That's because the input has a bigger dimension. It's not just a scalar. So at the end of the day, stability conditions for MIMO systems are not very different from those of single input, single output systems. All the ideas generalize. We want to put a little bit more attention at the concept of internal stability, because only looking at the input and the output mapping not necessarily guarantees that something is not blowing up in the middle of the of the loop. So we looked at this small gain theorem, which is interesting because it provides a sufficient condition that is easily verifiable for controlling closed loop stability, external stability. And we saw that internal stability does imply external stability, but the opposite is not always true. So now that we know how to define stability, we can talk about performance, which is the next step of a controller. And what does it mean to make a controller performant? A system design a controller such that the dynamics of the performance of a system are good. Typically, this means guaranteeing three big things. One is making the output of the system unsensitive to noise or to disturbances. And we call this disturbance attenuation or noise attenuation, and we will look at today what are specific formulations of, that quantify this attenuation. And then we look, unfortunately, we realize, as for the CISO case, that things are not just as straightforward as if we just could design the transfer function as we wish, because there are constraints that apply, or trade-offs in general. So this is a recap slide. It's the sensitivity functions, which we looked at several times already, and we looked at it several times because it's really relevant. What do sensitivity functions do? Sensitivity functions map all the possible relationships within a system. We said again that we have to distinguish between the input and the output ones because matrices typically do not commute, so we have to be careful at where we break the loop and what is the order of the operations we do. When we had the same conversation 4 weeks ago, we got to a result, and we said, look, at the end of the day, we could consider the whole control engineering as an exercise of shaping the loop transfer function of a system such that it avoids some obstacles. No? And we saw that these obstacles typically correspond at some barriers at the low end of the frequency range in order to guarantee disturbance attenuation, and that's because disturbances typically are defined at have a lower spectrum, a lower frequency range. And then there was another obstacle at the high frequencies, which was related to the measurement noises, the noises of the system. You want to attenuate those noises, that means the gain at those frequencies has to be low. But for single input, single output systems, this was relatively straightforward to look at because we had the loop transfer function, and the magnification, the gains at low or high frequencies were directly mapped to the magnitude of this loop transfer function. Now we saw that we have different transfer function, inputs, outputs, and they're not even transfer functions, actually. They're transfer matrices. So how are we going to extend the concepts we saw in the CISO case to this more complicated one? Well, this is the final result. This is what we'll get to in roughly 10-something slides from now. And it's something very similar, as you might notice. Guaranteeing disturbance attenuation still means avoiding a low-frequency obstacle, as well as guaranteeing noise attenuation still means avoiding a high-frequency obstacle. This time, though, we cannot just talk about magnitude of the open-loop transfer matrix, because we have input and output ones, and it's not straightforward how to determine them. But thanks to the introductions of norms, which we understood that intuitively represent gains of the transfer function or sizes of these systems, we will see that pretty much everything we said for the CISO case applies even to the MIMO case, just that you don't look at the open loop transfer function, but you look at the singular values, the maximum and the minimum one, which represent a worst case scenario, or let's say, instead of saying worst, let's say a scenario of maximum amplification and a scenario of minimum amplification. So as for example, in the CISO case, we defined the crossover frequency. Now, where the loop transfer function intersected the zero and logarithm scale, which is the unity response. Here we have a bandwidth. We have a family, basically, of behaviors, depending on the directions at which we're stimulating the system. So we will typically identify, if you want, an upper crossover frequency and a lower crossover frequency, depending on when the lower or highest the singular values of the system intersect the x-axis. So, and the conditions this time will be on the singular values again. So singular values play a fundamental role in determining the characteristics of MIMO systems. But again, the bottom line is going to be designing a controller to meet, to achieve performant behaviors of a system boils down to shaping the open loop transfer function of the system in some way. That is very similar to the CISO case. So what does it mean to have good performance? And we introduced the sensitivity functions, but we didn't really write what they map, right? So same old loop. If we start writing down the relationships between all the different variables, we can express the behavior of the output, of the tracking error, of the input and the disturbed input as a sum of terms that relate the various inputs of the system, disturbances, noises, and reference signal, to the internal dynamics. So, as we said before, having a good performance means we are insensitive to disturbances, we're insensitive to noises, and we track things well. What does this mean? Now, I'm using small letters for frequency domain, Laplace domain variables. You will find it like this in many textbooks. It's a little bit confusing. Typically, we use bigger letters, but just notation alert. These are all relationships that hold in the Laplace domain. So let's now pick one at a time, and let's understand what does it mean to have good performance as we just defined it. So say that we want the output to be, what, as we said 3 times, insensitive to disturbances and noises. Well, that's the transfer function of the output. So the output is the result of getting those 3 inputs, references, disturbances, and noises, passing them through those transfer matrices. And so how do we get the output to be insensitive to noise and disturbances? We just want the respective transfer matrices to be small, right? And what does it mean to be small? Well, we looked at how to quantify sizes of systems, and we found out that the worst case scenario, that is the direction of maximum amplification, if we want something to be small, it means we want that maximum amplification to be small. That maximum amplification is the maximum singular value of the specific transfer matrix. So in the case, for example, of output disturbance attenuation, we have that the transfer matrix is the output sensitivity matrix, as we defined in the slide before, times the plant. Well, then, having that small means that the upper singular value, which can be just re-expressed, these are just applying the definition and using the push-through rule, which is that simple property we saw a few lessons ago, has to be small. Small, what does it mean? Less than 1. Why? Because it's a gain. We said, no, the relationship between the norms of the inputs and the outputs are bounded by the singular values. Singular values are gains. So if you want the response to be small, you want that gain to be small. The maximum possible gain to be small, smaller than 1. And what about the noise? Well, it's the same argument. You always have a transfer matrix that maps the input, in this case the noise, to the output, and we want that maximum amplification to be small. So in this case, we're talking about the orange term there, which is the output sensitivity function, and we just apply the definition. We are looking, again, for the same properties, that is, the maximum amplification is small. What does it mean, small? Well, smaller than 1, because it's a gain. What about the inputs instead? So how does a disturbance or a noise affect the signal that actually goes inside the system and actually controls the system, the one that we called V, the perturbed input? Same concept as before. This is very, very, very linear as a way to find the conditions. You write down the relationship in the Laplace domain between inputs and outputs, and you just make the respective transfer matrices of the respective channels, that is N to V or D to V, small. And then you just apply the definition. So if we want good attenuation of disturbances to the input signal, well, we will have to make the maximum possible gain, that is the maximum singular value of the input sensitivity function, small. Small, again, what does it mean? Smaller than 1. Now, and the same applies, of course, for the input noise attenuation. One thing worth mentioning. These singular values are a function of frequency. So when we say small, what do we mean? Having the singular value small across all frequencies? Well, yeah, sure, ideally, yes. But in practice, we know that that's not possible. We recall from the single input, single output case that we didn't look at singular values, of course, but we looked at the sensitivity functions. We had similar arguments when we did the single input, single output case. The loop transfer function or the sensitivity function or the complementary sensitivity functions had these roles, mapped the relationship between noises and disturbances to critical parameters of the system. And we saw that the sensitivity function and the complementary sensitivity function, they're named like this. It's called complementary sensitivity functions because they're complementary. That means that if you sum them up at the specific frequency, they're equal to 1 in the single input, single output case. What does this mean? It just means that you can't just arbitrarily pick and choose what's the S and what's the T, because they have a relationship. They are not two independent degrees of freedom. So for the in this case, we will see that a similar concept applies, even if it is related to the singular values. The relationships are a little bit more messy. It's not as straightforward as just saying, the sum of the singular values has to be equal to 1, but the same concept applies. We cannot arbitrarily pick the singular value to have a shape that we design across all frequencies. So what do we do? Well, we are lucky, because what we deal with in the physical world allows us to distinguish between the lower frequency range and the higher frequency range. Why? Because typically what we model as disturbances that affected the input tend to have a frequency content that is at lower frequency content, while the noises typically are associated with higher frequency content. So we bypass this complementarity constraint by saying, hey, we just want some of them to satisfy properties in the low frequencies and in the high frequencies differently, so that we avoid the complementarity constraint. In order to have reference tracking, good reference tracking, instead what do we want? Well, again, it's the same argument as before. Ideally, the tracking error, which is the difference between your reference signal and your system output, ideally, you would like it to be 0 all the time, right? Because it means you're doing good tracking. You are following the reference signal. You are making the system do what you intended to do instead of how it would naturally behave. So it's a good thing to have the error be 0 all the time. That means we would like both the transfer functions, that is all the transfer matrices, all the transfer matrices that relate all the possible inputs to the E to be small. And we see that these conditions somehow are already included in the conditions we wrote before. So in order to get to some more practical, easy to look at conditions, principally to relate these properties on the singular values that we just determined to the open loop transfer function directly, we have to look at a few properties. And we will not derive these, but they are they derive from the definition of singular values, and the ideas are that the inverse of a singular value. So the singular value of your inverse matrix is the inverse of the singular value of the matrix, and you switch the upper and lower ones. There is a bound on the sum of the singular value. So if you have the singular value of a sum of two matrices, it's always possible to pick a singular value, it could be the highest, the smallest, or anyone in between, and bound the singular values of the sum by adding or subtracting the maximum singular value of the other matrix. And similar conditions apply for the product of matrices when you take the singular values. And it's important to say that there are pages of properties of singular values, and while it would be interesting to look at them systematically, not all of them will be useful in our case, so we will just introduce them as they come. And then if you look at the references of this class, you will see that there are nice summaries on your textbooks that if you are interested in having a comprehensive overview of all the possible properties of singular values, that's the place to go. So what does disturbance attenuation mean? We saw that depending on the output and input directions, we were looking at the maximum response of so here we have to take it slow a second. So we said that we wanted the maximum singular value of the transfer function to be small, right? To be smaller than a certain number. If we apply the properties that we just seen, the inverse one, and the sum, we can express the maximum singular value, applying the definition, as we can approximate it as just the upper singular value of the inverse of C. Why? Because if the first condition applies, then you can imagine as if you were PC is much bigger than I, so it's as if the I goes away, then the inverse just flips over P and C, P and P go away, so it can be approximated as the maximum singular value of the inverse of C. By applying the first property we saw on the previous page, we see that that's equal to the inverse of the singular value of the matrix. So where does this go? This means that If you want to have the upper singular value that is very small, that is achieved if and only if you have the lowest singular value of the controller that is very high. These might be confusing, but it's just applying the two properties to the definitions we saw before. And a similar thing can be written for the condition of disturbance attenuation at input, where this time we are just applying the definition, rewriting it, and bounding it using the summative property that we saw before. And we can see that making the maximum gain of the input sensitivity function small corresponds to making the lowest singular value of the loop big. Since we're talking about disturbance attenuation, in this case, we want these properties to hold at low frequency. So I think it's time to take a break. Yeah. Okay. So where were we? We were talking about how to now, hello? Find a seat, breathe, relax. You're in the magical world of control systems, where nothing can go wrong, unless things go wrong. Okay, so where were we? We were trying to evaluate the relation. Guys, we had a long break. I understand that it's morning, but let's get this continued. Are we good? Good. So, where were we? We were trying now to explicit a relationship between the conditions we found before that were really straightforward, because all we did was say, hey, let's write down the relationship, the mapping between all the possible inputs to the y's and v's, that is, the inputs and outputs of the system. And in order to prevent having a big effect of disturbances and noises, what we want is the gain of the corresponding transfer matrices to be low. That meant having the maximum singular value, that is, the maximum possible amplification across all directions of the input, to be a small value. Now, that helps us, but it would be even more helpful if we could summarize all these different conditions picked on the different transfer matrices into directly the open loop transfer matrixes. So how do we do that? We were looking at these first conditions on disturbance attenuation, and I messed it up a little bit because I put these things in the opposite order. So let's now just relook at it quickly. So what is going on? To have small effect of the disturbance on the input of the system, we want the maximum possible amplification to be a small number, okay? By using one of the properties before, we can see that we can bound this thing to be by the left and right parts. So here, this equality is just applying the definition, and we can see from the property that we wrote in the slide before that we can achieve this, this thing here. If it has to be much smaller than 1, the maximum gain, well, then it means that this term here has to be very big, sigma, the lowest singular value of CP. So assuming this, now let's go and look at the other relation. We should have flipped them over to make it clear. Assuming that we have the lowest singular value of CP to be very big, which is the first passage there, then we can write explicitly the definition of the transfer matrix between the disturbance and the output. And here we're doing a little bit we are considering, so we're saying if the minimum possible gain of the CP matrix is high, it means that CP matrix is big. That's we associated the meaning of singular values as the size of the matrix, right? That's the minimum possible gain. So having a big minimum possible gain means that the whole matrix is big. So there you don't really have CP. You have I plus PC, which is not the same thing, because we know that the products are not commutative. But so if you apply the push-through rule, and you just bring P on the other side of that, maybe it's easier if I rewrite it down. But the idea is, if you put the P on the other side, then CMP switch, and this is what happens. Actually, So if we have, let's just rewrite it. So from the first thing, we said that the lowest singular value of what? Of CP has to be high. This is to guarantee that disturbance to input is low. Now, if we assume this to be the case, and now we look at the relationship between the disturbance and the output, which is characterized by we said the biggest singular value, the maximum gain of the input sensitivity function has to be small, okay? So here we just write the definition, and we say this is equal to what? Well, the input sensitivity function, this was I plus what? Plus CP, right? Inverse, Y CP. So the easy mnemonic trick to remember these is just do them in order, starting from the previous one. So if you're looking at the output, if you just step backwards, you find first P, then C. It's PC. If you start from the input, you step backwards, you find the C first, and then the P. So it's CP. So what's going on here? Well, if we said that, I know, here we had, so the condition here was I plus PC, was this condition here. So the maximum singular value of I plus PC inverse P. So this is S output. I just wrote the wrong one. So if you bring this on the other side, you apply what we defined last time as the push-through rule, which is a rule that says, let's take, which is this rule here that I will rewrite. This is the push-through rule property. Call it as you want. So if you have a matrix A times a matrix B times I plus, let's say, what would be CD inverse, every time you push one matrix through the inverse, you have to switch the order of these two. So this is equal to A times I plus DC inverse B, which is equal to I. Now we're passing the A to the other side. We have to switch these again, plus CD inverse AB. Okay, so if we apply this here, this is equal to the maximum singular value of P, CP now, right? Because we need to invert it. Okay, now we know that the lowest possible gain of CP is very big. What does it mean? Somehow that this matrix is very big compared to what? To 1. So we can consider, that's why there was an approximation sign, as I to be negligible with respect to CP, because this is very big with respect to 1. I is the matrix equivalent of 1. So now we've got this that is approximately the biggest singular value of P, CP inverse. Now the inverse of a product of two functions is P inverse, C inverse. So these and these go away, and that's why this is sigma, the maximum singular value of C inverse, which, according to the first property that we wrote on the properties page, is exactly equal to the inverse of the lowest singular value of C. Okay, and this is the condition we had up there. So we just inverted the two equations. Sorry a second. Any questions? Yes?
I didn't understand why did you cancel
You didn't understand why?
did you cancel the identity? I didn't understand why did you cancel the identity matrix?
I didn't cancel it, but I'm considering it very small with respect to CP, because we said singular values are a measure of the size of a matrix, correct? Yeah. So there's we can bound the size of a matrix between the biggest and the smallest singular value. So if the big singular value is very big, we can't really say absolutely if the matrix is big or small. Yeah. But if the smallest singular value is very big, then we can tell that the matrix is big, because the minimum possible amplification that it will give is very big. So since the singular value is a measure of the size of the matrix, and you'll have to allow me this, then we can say, and I, the singular values of I, they're all ones, right? There's the identity matrix. So this is big compared to I. CP has a big size compared to 1. Therefore, we neglect this. This is negligible compared to. It's not actually that it goes to 0 that I canceled it. That's why we have an approximate relationship. It's not exact. Make sense? Does it answer your question? Okay, so where were we? Well, we cranked through the first one. Now we're looking at exactly the same thing for the other, for now the noise. How does the noise affect the input and the output? And we're writing down the definitions we took before, using those two properties, and we get very similar conditions that this time are related to the noise signal. As we said many times, the noise signal typically is associated at a higher frequency content, and you can imagine it, I don't know, as if it were a measurement noise. No? So we get these two relationships, and these represent the fact that, note as all these relationships are applied on the open loop transfer function, the L, either the input or the output L. Okay? So we passed from having conditions on the closed loop sensitivity functions to conditions on the singular values of the open loop transfer function. And sometimes directly on the controller. For example, you might notice that the relationship between the noise and the input is nothing we can really do anything about, because it boils down to having the lowest singular value of the plant that has to satisfy a certain condition. And it's not like we can change the plant. We can design a controller. So this is something that might sometimes turn out to be a problem. So, okay, we looked at this basic idea of making small the transfer matrices between the unwanted inputs and the desirable outputs. But there are even other considerations to keep in mind. And one, which is the topic of our last half hour of class today, is that of robustness. So all of that, all the conversation we had until now works perfectly. It stands, it's logical, if you have a perfect idea of what's going on. That is, you model your plant exactly as it should be. Now, turns out that most of the times this is not the case. There's always an uncertainty on what's the behavior of a plant. And we'll talk about it in detail later. But now, let's just suppose that we can represent the real plant, what is actually going on, like the real system you're going to be dealing with. It's not just the nice transfer matrices that you wrote down after whatever test or whatever modeling that you did. But there's actually an uncertainty, a model uncertainty associated with it. And let's suppose we can write it like that. The model uncertainty is somehow quantified in delta. We'll talk about later in detail different ways to quantify the model uncertainty. Now, if we just look at what, of course, since here we're talking about performance, but we said before performance you want stability. So what if you have an erroneous knowledge of your model? Is the system still stable, closed loop? Supposing that the controller C that we designed works for the nominal plant, of course. When you design a controller, you design it with the model you have. So if you just included the uncertainty at the real plant, and you do apply some tricks, I don't know if you recognize those matrix equations, what turns out is that the some norm of the perturbed output sensitivity function has to be smaller than 1. And that brings a constraint on the output open loop function that is exactly the opposite as the one that we wanted before. So there are trade-offs going on. You can't just achieve everything perfectly, otherwise life would be too easy. And in order to avoid actuator saturation, which is another problem in real life, we don't really ever mention it when we do our calculations, but you can imagine that every time you implement a control system, you don't have infinite amount of capabilities to control your system. Your input, here what we talk about are logics. You say, I want my input to be designed such that things happen. But then it will produce a signal. That signal might have some physical, it might be a voltage, it might be a displacement, it might be something, but it's a physical quantity that has to be actuated on the actual plant. So you're transforming a logic into a physical force or whatever it is. So the device that does this it might have limits, physical limits of behavior. For example, a saturation. You imagine you're having a valve that you're using to control the flow rate of water or whatever it is, or some chemical into a distillation process or some chemical plant. It's not that you can infinitely open the valve. The valve, it's open or it's closed. After it's open, you can't open it more than maximum open, right? That's input saturation. So whatever control logic you're going to write down that makes the valve open at 300%, well, guess what? That's not going to work because your valve can only open at 100%, right? And there are similar restrictions of these kinds, for example, on the rates of the input as well. Imagine a big, nasty valve now for a very big power plant. You can't just turn it as fast as you want, right? There are even physical limitations that we have to account for. So by putting all of this together, we get the result that we had before. Please note, I noticed a typo on this slide basically half an hour before coming to class. So if you have printed out these slides before half an hour, you'll see that here the signs are inverted. They're minus, minus, smaller, smaller. That's quite the opposite, okay? So the idea is now summing up all of this together, we get back to the result we saw at the very beginning, which is the same thing as for CISO systems, just that we now have to think about the singular values, the lowest or the highest singular values of the open loop, in this case, output transfer matrix. So again, the conclusion, what's the conclusion? Is that all control systems is about shaping this function in order to avoid some blocks at low and high frequencies that depend on disturbances and noises of your specific application. Of course, when you go and actually design the system, you want to know what WL and WH are, and there are full strategies of control that are based on frequency shaping. And we will see, we'll touch upon these later on when we go and do the synthesis of controllers. So here I will just hand wave this a little bit and make some parallelisms with the single input, single output case. So we said that, so all of this was to guarantee performance. If you want good disturbance and noise performance, you have to satisfy those requirements. Very well. Now, what if instead, so we know that there are other limitations that are of fundamental nature. We looked at, in the CISO case, that the sum of the S plus T has to be equal to 1. Well, the same thing applies here. Only that it translates into singular values in our relationship that's a little bit more complicated, but the point applies in the same way. That is, you can't arbitrarily shape your singular values as you want. As we saw for the single input, single output case, right-hand plane unstable zeros, non-minimum phase zeros, as well as unstable poles, cause problems to the plant. The way we saw it in the single input, single output case was that, remember the Bode integral, the principle of conservation of dirt? We said that the integral of the sensitivity function had to have a specific value, okay? And that value was something that the lower it was, the better, because it provided the good performances that we wanted. But if you added unstable poles or zeros, this amount of dirt increased. So it was bad to have right-hand poles and zeros. Similar conclusions can be applied for the MIMO case. A right-hand plane zero, what it does, it limits the upper bandwidth of your system. And a right-hand plane pole increases the lower bandwidth of the system. So it moves that area of, it determines this area, puts constraints on where the intersection of these two curves can go with the x-axis. And of course, we know, as we've seen before, that poles and zeros in the MIMO case they're not absolute, right? They depend on the direction. So these things that we're saying really are not as powerful as for the CISO case because they only apply in the direction of the zero and the direction of the pole. And we saw another big thing in the CISO case was the time delay. We saw the time delays were ugly because they increased the phase of the system, and it was as if we were adding unstable zeros to the system. Again, similar considerations apply for the MIMO case, but not really. It's difficult to say anything about the effect of time delays on MIMO systems. Actually, the probably surprising thing is that time delays can actually be good for a MIMO system. There are some considerations, some examples, we can probably look at it some other time, where a time delay can make an uncontrollable MIMO system controllable. It can actually increase the decoupling between the different channels, therefore change basically the condition number that we defined before. So bottom line is time delays, we don't really know. We have to evaluate on a case-by-case basis, basically. And then the principle of conservation of dirt applies, of course, even to the MIMO case. It's just that, again, the expressions are much more nasty. They are based on singular values. They only provide inequality constraints and not equality constraints, so it's not worth looking at them because we can't translate them into practical, useful, let's say, tests for the MIMO analysis, but the concepts apply. Okay, so now we can talk about robustness. We looked at when is a system stable? How can we make it, what does it mean to make it performant? But we saw at the end of the robustness analysis that actually there were some very important practical things that need to be taken in consideration and affect the whole conversation we just had. And I think everything can be really summed up. If you want to remember one thing from this class, just remember that all models are wrong, but some are useful, okay? Which is a citation from George Box. And what does it mean? We could start a philosophical debate on this, but the bottom line is that we don't really know what is going on. Nobody really knows what's going on. A model is not an actual description of what is going on. A model replies to the question, everything goes as if it was driven by this mathematical formulation. And that as if is the most as if of history, okay? It's not like the model really is what's going on. It's just a blanket you put on top of it, and it seems like it has the same shape. So some could say that the universe of mathematical modeling has nothing to do with the universe of physicality of things, but we will just say that it's impossible to have a perfectly accurate model at all frequencies, even because of practical limitations. Most systems, the ones that are governed by transfer functions that roll off at high frequencies, are very difficult to analyze and to map. So there is something called system identification, which is the process of, let's say you want to reverse engineer something, okay? So you're an engineer working at some company and you find a box that you don't know how it works. How do you reverse engineer it? How do you know how it works? Well, you need a map between the inputs and the outputs, a transfer function. So what do? You use the concept of I send the sinusoids at every input and I wait for steady state, and you draw a frequency response of the signal. That's how you identify a transfer function. But at high frequencies, things don't behave appropriately. The outputs are very small, typically very fast. Phase information is completely lost. So even in the best case scenario, when we're modeling something that is very well known, I don't know, a mass spring damper system, I get it that the universe of modeling is different from a universe of physicality, but there are some things that we nailed down pretty well. Still, typically high-frequency behaviors might be badly described. There might be dynamics that are not described in the model. There might be parameters of the plant that change in time. So the model was good at the beginning and might not be good after 100 hours you're using it. You're using the physical system. And so the bottom line is that whatever the reason is for the mismatch, a mismatch has profound implications on the design of a controller. We call the difference between what is the output predicted by a model of the system and the actual output of the real system when you send the same input as uncertainty or model uncertainty. And there are different ways to represent uncertainty. So one could ask the question, yeah, but if I know what I'm missing, if I know what I'm not describing, high-frequency behaviors or some dynamic that is simply not useful to the engineer. You're an engineer, your objective is controlling the system, not making the most possibly exact description of what's going on. You just want to focus on those aspects that are most relevant to the design. So whatever the reason is for model uncertainty, the way we write down the mathematical models are not related to the reason for which the uncertainty comes. They're just mathematical formulations, and the objectives is to make them as tractable as possible. And we will see that with simple formulations, we are lucky enough to be able to describe uncertainty on some frequency ranges that turn out to be a good representation of what happens in most models in reality. But again, here we're talking about uncertainty. So we have to never consider just one plant, but a family of plants. Okay? So you'll say, if this is my nominal situation, well, it could be anywhere between nominal plus minus or something. And let's see how something is defined. So some terminology before starting. So let's suppose we have now, as usual, this is the loop you've seen a million times, but it's even made more simple because now we're forgetting about noises, disturbances, all of that. Let's just focus on plant uncertainty, okay? You don't have a good model of your system. You think you do, though. You have a P that is your nominal plant, okay? And then you have a controller. And you do all your homework and you design your controller such that you stabilize the nominal plant. Note the distinction between nominal and real. Now, we define delta, which is, of course, a function of frequency, as all the other entities that we're going to define, as the uncertainty block. And then we define these two matrices, W1 and W2, that are... Did I say something really wrong? No? That are weights for the uncertainty, okay? So why are the weights necessary? Because we'll see later on that it's really easy to treat mathematically and apply the theorems that we already know if that delta has some very nice properties, like it's a unit infinity norm or stuff like this. Okay, that just makes our considerations easier. But then to make it realistic, you want to weight it with two functions so that you can actually represent its effect it has on the full system. So for now, let's just call W1 and W2 weighting functions. And while delta is the modeling error, we call uncertainty, we can consider it always as applied as omega-1 times delta times omega-2. Okay, so the uncertainty is scaled and with respect to these weighting functions. So depending on how we relate the uncertainty to the nominal plant P, we get completely different representations of uncertainty. What is the right one, what is the wrong one, depends on what you're doing. So there is no exact recipe here to use. What I'll show you is the most common ways to represent uncertainty, and I will show you a nice big table where there are the 30 least common ways of representing uncertainty, and each one is described, tells you when it works well. And you just use that table as reference to understand, and depending on your specific situation, what model uncertainty representation fits best your needs. So typically, okay, so just keep in mind that sensitivity functions are the same thing, but they're all defined with respect to the nominal plant, okay? Because that's the only thing we really know. Now, the first thing we do is, these are some qualitative examples, no? So we will talk mainly about two types of uncertainty, which are the additive and the multiplicative representation of uncertainty. That is, we take the nominal plant and we either sum uncertainty or we multiply it by uncertainty. And this has different repercussions on what is it that we're actually imposing it to be. So for example, if you add additive uncertainty, and we'll go into the details, we'll look at it a little bit better later, just to give you an idea of the final result. You might recognize that as a Nyquist plot, no? So an additive uncertainty description, what it's saying is the more you go high in frequency, the more you are perturbing your system. In the sense, the more your system is uncertain, the more you don't really know where it's going to be. It could be where the nominal plant is, but it could end up being anywhere where the big circles are. Okay? So, well, this is one way of describing uncertainty. Sometimes you use multiplicative uncertainty instead. That it's nice because it puts bounds in the frequency domain. And it represents, let's say it's the graph on the right. The center line would be the actual model, the nominal plant. The one the nominal plant is this center line here. And, but really the frequency domain behavior varies. And it varies more, it's more uncertain the more you go at high frequency. Why? Because typically it's difficult to grasp exact information at high frequency from a system. And this is something that, I mean, if you ever test it in practice, you will notice how this thing, like this graph here on the right, is really a very dear friend. It always comes up like this. So first, let's talk about what is it that we can say without making making the least possible number of assumptions, okay? So we call this unstructured uncertainty. The structure here relates on what is the mathematical formulation we're using to relate to delta and P, okay? Suppose we don't say anything. We keep it as an open question. What can we still say about uncertainty? Well, we have a family of plants, but we don't really know how the uncertainty relates to that plant. But do you remember internal stability that we defined roughly at, slide 10 today? The same exact idea can be applied here. And we can say, look, the system is internally stable when that matrix is invertible, when the four independent matrices, transfer functions, are each one stable on its own. What else can we say? Not really anything if we don't make other hypotheses. But this case is important because it served as the basics for proving all the other possible structured uncertainties that come to your mind. So we will always go back to this, basically. Whatever consideration conclusion will come out later, it's always based on apply this condition. Make sure these transfer functions are all invertible. They're all stable. So the easiest way is talking about additive uncertainty. What does additive uncertainty tell us? It tells us that the way we are modeling our mismatch between practice and theory is by adding to the nominal plant a weighted uncertainty. It's the simplest possible relationship for the first maybe you can write down. Well, then if we apply the internal stability condition and we crank out the math, all we're doing is we're just substituting P plus W1 delta W2 in place of the big pi here. So you get big expressions. If we look at what are the conditions for each one of them to be stable, applying the small gain theorem, that is very nice, because you can reason about stability of matrices by only looking at their norms and not going and looking at the poles exactly, then it can be shown that a loop described like this is robustly stable only if the infinity norm of this term here is smaller than 1. If the maximum possible gain of the uncertainty multiplied by C as the output of the sensitivity, the output sensitivity function is smaller than 1. And the idea, how do we achieve this? There's a full proof in references. But the idea is we get these, we apply internal stability conditions, and we just use the small gain theorem that we defined before to actually converge to a condition. A similar thing can be said about multiplicative uncertainty. And this time, multiplicative uncertainty is sometimes preferred to additive uncertainty because it's a kind of uncertainty representation that sticks through all the loop, in the sense that if you have multiplicative uncertainty on the plant and you crank it through your loop, you will see you'll have the same kind of multiplicative uncertainty even on the sensitivity functions and stuff, so it's simply more easy to use on a mathematical level. It's convenient. And basically, this is more of an idea of saying, look, I model uncertainty as a percentage mismatch, if you want, with respect to the nominal plant. I'm not just adding components, but I'm saying it's whatever they are plus minus something %, basically. That's what we're writing down with the multiplicative uncertainty. Of course, here we're always assuming that the weights and the uncertainty matrix are stable from themselves. Actually, that's not a strict requirement. One can go nuts and just make very arbitrary, complex, nonlinear functions or some unstable uncertainty generators and things like this. All the results must be adapted and extended, but it's possible to do it. It's important to notice, by the way, that uncertainty not necessarily describes something you don't know. For example, say you have a linear time invariant system and you're doing all your you can well approximate your system as a linear system, and so you can use all the theory that we know. But you know for sure that there is a nonlinear component to it. You can describe the mismatch between the linear model you're using. Again, models are used just for convenience, right? So you know something is nonlinear, but it's easier to treat it in a linear way. Just model it as linear, okay? But then you'll say, but that's not the real deal, so it's gonna break down. I mean, it's not gonna work, the controller you do. Well, if you represent the effect of the nonlinearity, that is the mismatch between the actual thing and what you model as uncertainty, well, if you apply then tests on robust performance and robust stability, you will still be able to do a stabilizing controller. So in the case of multiplicative uncertainty, we get this a similar condition as before, actually very similar, but the condition now is applied on the weighted output to complementary sensitivity function. So this was just a taste to tell you, look, the problem is a real one. Like, this will happen always, every single time you will go and work with a real system. You'll enjoy it with the DuckyBot. You will see that although it's a very simple system, it's very tough to get an exact model that is usable to predict the behavior of it because of, for example, frictions that you can't model very well, bumps on the road, you name it, the mechanical components of the system that are not perfectly symmetric because, you know, they're manufactured, so maybe a motor is slightly different from the other, even if they're the same model and brand. Maybe the wheels are one smaller than the other. Maybe when somebody assembled it, it's slightly asymmetric. Maybe the center of mass is not exactly at the geometrical center of the frame. These are all assumptions you do when you do the modeling because just when you hooked it up, you just moved the battery a little bit. These are all models uncertainties. It happens all over the place. So how can we choose what is the best way to represent this uncertainty? Theoretically, you can represent it as you wish. These are a number of different ways that have been studied in literature. You're not required, of course, to know all of this. This is just for your interest to understand that it's not just either you sum or you multiply, but you can actually get into more on different structures, and they well represent different physical phenomena. And overall, we can conclude by saying that the way you can test for robust stability is assuming you are given already a system that is nominally stable, that is a system that has the plant and has a controller that has already been designed to make that plant stable, okay? The nominal plant stable. And then you're given a model set. A model set is a way of saying what is the family of different models given the uncertainty that you're choosing, given the way you're choosing to represent uncertainty. So instead of working with a single plant, you work with a family of plants. So if you're given a nominally stable system and you're given a model set, then you can check for closed loop stability by one of these tests, depending on how you modeled it. So, in summary, wow, we finished the class today. Can't believe it. Model uncertainty is always there. There's no way to get away from it. Sometimes you might not care. This is it's very important at this point that for the first time we're making a step from the theory to the actual practice. No? In engineering, you care about achieving your specifications, not about doing the perfect analytical resolution of whatever it is, proof and the rigorous stuff. So uncertainty is always going to be there, but you'll have to make choices. You have to make calls. You have to decide what is the best way, what's the intersection of the simplest possible way, but at the same time the most effective to represent the specific problem I have at hand. There is no right or wrong answer. It depends, okay? So you'll have to be aware of the existence of the problem, and then depending on the specific application, you'll have to go and choose which one is your best way of doing things. And typically, simulation and testing helps. Simulation more than testing because if you do mistakes, you don't break stuff. We could start a full new course on simulations, but let's leave it at here. So what else to say? I think we're all set for today. I would just like to say that in the next classes, we'll move on towards designing controllers. So we'll stop talking about how to analyze the different stuff, but we'll actually see how to design controllers to achieve this stuff. And as a very final note, I would like to remind you that there's not going to be class next Friday, and not even the Friday afterwards, because we have 2 Easter Fridays, basically. So enjoy your vacations, and see you in a few weeks.